85,000 feet above the Earth, the sky isn't blue. It is a deep, bruising purple that fades into the infinite black of space. It is a place of absolute silence. But inside the cockpit of the aircraft cutting through this void, it is anything but silent. The hull is groaning, the metal is stretching, the engines are swallowing 100,000 cubic feet of air every second, compressing it until it becomes a controlled explosion. This is not a spaceship. It is a plane designed in the late 1950s using slide rules and pencils. It was built before the moon landing, before the microchip, and before the internet. And yet, it is faster than a rifle bullet. It flies so high that standard missiles can't reach it. It flies so fast that the air friction alone heats the cockpit glass to 600 degrees Fahrenheit. This is the Lockheed SR-71 Blackbird. For 30 years, it was the ghost of the Cold War. It flew over Vietnam, North Korea, and the Soviet Union. 4,000 missiles were fired at it, not one ever hit. But the story of the Blackbird isn't just about speed. It is a story of desperation. It is a story of a plane that was so impossible to build that the CIA had to steal the materials from the very enemy they were trying to spy on. It is the story of a machine that leaked fuel on the runway, exploded its own tires, and required its pilots to wear spacesuits just to survive the commute. Today, we are opening the classified files to understand why, 60 years later, no one has ever managed to build anything better. Welcome to Shadowworks. The story of the Blackbird begins with a failure. In the 1950s, the CIA believed they were untouchable. They were flying the Lockheed U-2 spy plane, a glider with a jet engine, over the Soviet Union at 70,000 feet. They thought Russian radar couldn't see them, and Russian missiles couldn't reach them. They were wrong. On May 1, 1960, a Soviet SA-2 missile exploded near a U-2 piloted by Francis Gary Powers. The plane disintegrated. Powers was captured. The United States was humiliated on the global stage. President Eisenhower grounded the U-2 flights. The CIA was blind. They needed a new way to see behind the Iron Curtain. They needed a plane that didn't just fly high. They needed a plane that could outrun physics. They turned to Clarence Kelly Johnson, the legendary head of Lockheed's Advanced Development Projects, better known as the Skunk Works. Kelly Johnson was a genius, but he was also a realist. He knew that to survive Soviet airspace, the new plane couldn't just be fast. It had to be a ghost. It needed to fly at Mach 3, 3 times the speed of sound, and sustain that speed for hours. To put that in perspective, most fighter jets can hit Mach 2, but only for a few minutes before they run out of fuel or their engines melt. Kelly Johnson was proposing a plane that would cruise at the speed of a bullet for thousands of miles. The project was codenamed Archangel. But as the engineers at Skunk Works started the math, they realized something terrifying. Building the Archangel wasn't hard. It was impossible. When you move through the air, you create friction. Friction creates heat. At Mach 1, the heat is manageable. At Mach 2, aluminum starts to soften. At Mach 3, the air friction is so intense that the leading edges of the wings reach 800 degrees Fahrenheit. The exhaust section hits 1,200 degrees. If you built the SR-71 out of aluminum, like a Boeing 747 or a P-51 Mustang, the plane wouldn't just fail. It would melt into a puddle of molten metal before it even reached its top speed. Steel could withstand the heat, but steel is heavy. If they built it out of steel, the plane would be too heavy to take off. They needed a metal that was as strong as steel, as light as aluminum, and could survive the temperatures of a blast furnace. There was only one element on the periodic table that fit the bill: titanium. Titanium is a wonder metal. It is incredibly heat-resistant and incredibly strong. But in the 1960s, it was also a nightmare. First, it was brittle. If you dropped a sheet of titanium on the floor, it could shatter like glass. Second, it was impossible to machine. It chewed through drill bits and saw blades. Skunk Works was going through thousands of drill bits a week just trying to make holes in the frame. But the biggest problem wasn't manufacturing, it was supply. In the 1960s, the United States didn't have much titanium ore. The world's largest supplier of the ore needed to build the CIA's spy plane was the Soviet Union. So the CIA had to pull off one of the greatest ironies of the Cold War. They set up a network of shell companies in third world countries. They posed as civilian firms looking to buy titanium for pizza ovens and golf clubs. They bought the metal from the Soviets, shipped it to the US, and drove it quietly into the Skunk Works facility in Burbank, California. The Soviet Union was unknowingly selling the United States the very metal that would be used to build the spy plane that would spy on them. But getting the titanium was just the start of the headache. Using it created engineering problems that no one had ever solved before. Because the plane would heat up so drastically at Mach 3, the entire airframe would expand. The SR-71 literally grew by several inches in mid-flight. If the engineers bolted the fuel tanks together tightly on the ground, the expansion at high speed would rip the rivets apart and the plane would explode. So they did something insane. They designed the plane to be loose. They built the fuel tanks with intentional gaps in the joints. They put rubber sealant in the cracks, but on the ground, when the plane was cold, the sealant didn't seal. This meant that on the runway, the SR-71 leaked. It bled fuel constantly. It sat in a puddle of its own making, dripping highly flammable aviation fuel onto the tarmac until the moment it took off. Only when the plane reached high speeds and the heat expanded the titanium panels would the gaps close, sealing the tanks. This required a special kind of fuel. You couldn't use standard jet fuel. If you dripped standard JP4 on a hot runway, you'd have a barbecue. Shell Oil had to invent a new compound called JP7. It had a flash point so high that you could throw a lit match into a bucket of it, and the match would just go out. It was safe to leak, but it was incredibly hard to ignite inside the engine. To start the engines, the Blackbird used a chemical injection called triethylboron, or TEB. TEB is a pyrophoric chemical. That means it explodes instantly upon contact with air. Every time the pilot lit the afterburners, a shot of TEB was injected into the engine, creating a distinctive green flash. That green flash became the signature of the Blackbird. It was the color of dangerous chemistry. The heart of the Blackbird was the Pratt & Whitney J58 engine. To this day, it is the only engine of its kind ever mass-produced. It was a hybrid, part turbojet, part ramjet. But the engine itself wasn't the most critical part. The magic was in the inlet. Look at the front of the SR-71 engines. You see those massive sharp cones sticking out? Those are the inlet spikes, and they are the reason the plane could fly at Mach 3. Here is the physics. A jet engine cannot swallow air moving at supersonic speeds. If air enters the compressor at Mach 3, it will tear the blades apart. The air has to be slowed down to subsonic speeds, below Mach 1, before it touches the engine. The spike was designed to create a shock wave. As the air hit the spike, it created a cone of pressure. By moving the spike forward and backward, controlled by an analog computer, the Blackbird could position that shock wave perfectly inside the inlet. This process slowed the air down and compressed it. By the time the air reached the engine, it was moving slowly, but it was under massive pressure. At Mach 3.2, the engines themselves provided only 20% of the thrust. The other 80% came from the inlet design. The engine essentially became a flow inductor for a massive ramjet. But this system was temperamental. If the spike was in the wrong position, even by a fraction of an inch, the shockwave would be spit out of the front of the engine. This was called an inlet unstart. An unstart at Mach 3 is one of the most violent things a pilot can experience. Instantly, one engine loses 80% of its thrust, while the other is still pushing at full power. The plane would violently yaw to the side. The pilot's helmet would slam against the canopy. The force was enough to crack vertebrae. The pilot had seconds to manually adjust the spike and restart the airflow, or the plane would break apart in mid-air. Flying the Blackbird wasn't a smooth cruise. It was balancing on the tip of a knife for hours at a time. Because the SR-71 flew at 85,000 feet, the pilots were technically flying in space conditions. If the cockpit depressurized, their blood would boil instantly. So, they wore full pressure suits, the same suits used by the Gemini astronauts. They breathed 100% oxygen. They ate tube food through ports in their helmets. But despite the danger, the men who flew the Blackbird, the sled drivers, loved it. Because they had a superpower: speed. In 1986, when the US bombed Libya, SR-71s flew over to assess the damage. Libya fired surface-to-air missiles. In a normal plane, you deploy chaff, you bank, you dive. In the SR-71, the defensive maneuver was simple: push the throttle forward. The pilot would just accelerate. The missiles would streak upward, burn out their fuel trying to catch the Blackbird, and fall harmlessly back to the desert. The SR-71 was the only aircraft in history that didn't just outrun the enemy, it outran the timeline of the engagement. There is a famous story from pilot Brian Schul. He was flying over California, listening to radio traffic. A Cessna asked air traffic control for a ground speed check. 90 knots, a Twin Beach asked for a check. 120 knots. A Navy F-18 Hornet decided to show off. Dusty 52, ground speed check. 620 knots. Then Schul keyed the mic. Aspen 20, ground speed check. The controller paused. Aspen 20, I show you at 1,942 knots. That was the reality of the Blackbird. It was operating in a different dimension of speed. On its final flight in 1990, the SR-71 broke one last record. It flew from Los Angeles to Washington, D.C. It covered the entire continent of North America in 64 minutes. The average speed was 2,124 miles per hour. The SR-71 was retired in 1998. But here is the haunting question. That was nearly 30 years ago. Technology has exploded since then. We have stealth, AI, quantum computing, so why is the SR-71 still the fastest air-breathing manned aircraft ever built? Why haven't we built an SR-72? Part of the answer is strategic. Spy satellites became better. They don't put pilots at risk, and they can stay in orbit for years. Drones like the Global Hawk can loiter for 30 hours. But the real answer is physics. The thermal thicket, that heat barrier we talked about, gets exponentially worse after Mach 3. To go Mach 4 or Mach 5, titanium isn't enough. You need exotic ceramic composites. You need scramjets, which are notoriously difficult to stabilize. The SR-71 sat in the Goldilocks zone of high speed. It was just fast enough to be invincible, but just slow enough to be built out of metal. There are rumors, of course. Lockheed Martin has hinted at an SR-72, son of Blackbird, a hypersonic drone capable of Mach 6. But as of today, it remains a shadow, a concept art on a website. The Blackbird remains the king. When you look at an SR-71 in a museum today, you are looking at a miracle of analog engineering. It was a plane that had to be invented from scratch. They had to invent the fuel, the oil, the tires, the paint, and the tools just to build it. They had to hustle the Soviet Union to get the metal. They had to overcome the atmosphere itself. It was a machine born of paranoia and fear, a weapon of the Cold War. But it became something else. It became the ultimate expression of brute force engineering. It proved that if you have enough titanium, enough fuel, and enough courage, you can make a brick fly faster than a bullet. We may never see a manned aircraft like it again. The skies are silent now. The sonic booms are gone, but somewhere in the dusty archives of the Skunk Works, the blueprints are still there, waiting for the day we decide to push the throttle forward one more time. I'm Shadowworks. If you enjoyed this deep dive into the archives of failed engineering, make sure to hit that subscribe button. Next week, we are looking at the Soviet attempt to build a flying aircraft carrier that ended in a ball of fire. You don't want to miss it. Check out this video on the screen right now about the Soviet Caspian Sea Monster, another giant that flew too close to the water. Clear your baffles. I'll see you in the next one.